Hello and welcome to Toddcast number 31. Um, Continuing on in chapter 7 material, but changing from substitution reactions, nucleophilic substitution, into something known as elimination reactions. And as the name implied with substitution, you're substituting one thing for another. This one, maybe it's not as obvious to see, but you're eliminating a few atoms or a few groups or a few bonds from a molecule. So what we mean by that is, if I consider this molecule, and we learned 1, 2, 3, 4, so 5, 2-bromopentane, we learned that in one instance, this OH minus can come as a nucleophile and substitute in. That can definitely do one thing. That's one type of reaction. But as we will learn, sometimes reagents can do multiple types of reactions, and you have to modify the conditions, the temperature, the solvent, other factors to influence it to go one reaction or the other. So in this case, we're not actually going to do substitution. Instead, we're still going to have the OH minus acting, but it's going to act in a different way in that instead of attacking a carbon, it's going to deprotonate. And so there are hydrogens on this carbon and this carbon. And the reason I choose these is because they are next to the carbon with the bromine. And so if I can eliminate that H and that Br, then I have this scenario here where both this carbon here lack a bond. So we put a double bond there. So let me go into the details of it. So I'm going to erase this. I'm going to start from scratch. Tell you a strong base, and a strong base that isn't necessarily a great nucleophile. If it's a high enough temperature, then it can go in and take an H, have the electrons kick over and kick off the Br. So you're going to remove an H and a Br, just as mentioned. So when we do that, and again, I want to specify the exact H that was taken off and how it happened. So I'll do this one this time. That takes the H there. Those electrons go in to form a pi bond there, kick out the Br. So it's almost like you take the H, then substitute electrons from the H into the pi bond, which then kicks out the Br. Known as E2, so just like the SN2, means it depends on both the base and the electrophile reacting at the same time. So it's considered a reaction. This comes in, knocks it over, kicks the Br out. The other type that we have, so just getting right into this, E1 done in base, just like, or E2, excuse me, just like we had SN1, SN2, we have E1 and E2. So strong base does elimination by an E2 mechanism. Strong acid, on the other hand, is going to do it, but by an E1. So just like with SN1, the leaving group will leave, then we'll carry out whatever the reaction is. So a couple things, and I probably should have put this up here, but heat helps. And the reason heat helps is sigma bonds, 2 sigma bonds, are more stable than a double bond and the bond between H and Br. So you're breaking stronger bonds to form weaker bonds. So if you pump heat into it, you can drive it uphill and form the alkene. So you're actually going from a more stable to a less stable product, more stable reactant to less stable product. So you need the heat. So that's why a lot of times elimination can be given away. Like the telltale secret is the heat. It forces the unfavorable reaction to go. So let's consider this for a moment. So like we alluded to with the rearrangements we were talking about, and with making OH a better leaving group, both of those popped up last time, we're going to look at the same things here. This is going to go and take an H plus from sulfate, so from sulfuric acid and turn into hydrogen sulfate. When we do that, we're going to end up with this compound with an OH2 plus charge, which can then have that leave. So we looked at this, and I'm going to say it's an equilibrium at this point. We looked at this towards the tail end of last lecture. We talked about rearrangement. So let me just double check, make sure this is a good one. This is tertiary, so it's going to stay. We then will get elimination. So I'm going to draw the H again in purple, just to emphasize. And there's two H's here, so I'll put 2 along with the methyl group that's here. Make that a little bit longer. And so if I'm going to draw this haphazardly by just saying it magically falls off, but the solvent must come in and pick it up. But for now, I'll just draw it like this. This H is going to lose its electrons to here, so you end up getting an H plus and a double bond. So the same H plus that went on in the beginning, the strong acid, is catalytic. It's regenerated in the end. The reason this works the way it does is, again, we have heat pushing it uphill, but we also have a case of sulfate being an absolutely horrible nucleophile and not being able to attack. So if you use an acid with H connected to a really good nucleophile, so let's say you use HBr, HI, then there's a chance that the Br or the I minus would substitute for the water. So just a point of interest, we're choosing something with a terrible nucleophile. So typically sulfuric acid with heat, nitric acid with heat are going to be ones that you don't have a nucleophile, so elimination is your only reaction. So let me go ahead, I'm going to erase everything I have to make room for drawing coming in, but that's a mechanism, as it's called. Okay, so there we go. So your product in this case, you're going to remove the H and the OH. So here's my H here, or my OH here, and here's my H here. Going to group them both. I'm going to leave the double bond there. So that's your double bond forms here. Okay, so for this, just that introduction, substitution, one thing substituted for another. Here we're removing an H and a Br in neighboring carbons. Here we're losing an H and an OH on neighboring carbons. So questions that will pop up is, why do I choose H from here and not from here or not from here? And I could have chosen from these. In fact, that's going to be a minor product I should consider. But we typically go for whichever one is more stable, more substituted. So we want a double bond to be internal. So here rather than here. And here rather than here. So we want as many alkyl groups on it as possible. So this is tri-substituted as opposed to di-substituted. This is di-substituted as opposed to mono-substituted. So hopefully that makes more sense in a second here. But a few things then. So when I come to a question like this, the first thing that should catch my attention is the heat. Heat implies that I'm driving the reaction in an uphill fashion. So the fact that I do that, here's my H and my Cl. It's a base, it's a strong base. So this is an E2 reaction. Okay, not what the question is asking me, but I still just want to emphasize what I'm dealing with here. So my E2, these carbons, everything is sp3 hybridized because there's no pi bonds, but in the end, you get 2 sp2 hybridized carbons. So during this reaction, what change occurs in the hybridization of the carbon bearing the chlorine? So this carbon right here is starting out sp3 with 4 things attached and turning into sp2 with only 3 things attached. So sp3 to sp2, best answer. A is an awesome answer, although it hasn't popped up yet. So hopefully it is right there. Okay, so let's look at this E2 first. Let's eventually look at the E1. But for now, the E2 reaction requires a base, as mentioned. Oops, did not mean to do that. So I'm going to just say R1, R2, R3, R4. They could be H's, they could be methyls, ethyls, just to have some distinction. The H and the Br have to be anti to one another. Anti-paraplanar is what the term is, but anti, just like we had with Newman projections. So again, all these things we talked about early on and all these structures and terms were the foundation of what we need now. So when I say anti, you know, oh yeah, anti is up on one and down on the other, both in the plane. So everything is coplanar. The reason you need that is because you absolutely have to have the orbitals lined up the right way for this reaction to work. So we're going to call this the alpha carbon, the one with the leaving group, and this the beta. So there's going to be a double bond formed because we lose a leaving group from alpha and an H, losing its electrons to the alpha-beta bond. So the electrons on beta connected to an H will turn into the pi electrons, and the electrons between the alpha carbon and the leaving group go with the leaving group. So anti, H, and leaving group. So has to be anti. Strong base will come in. That's what we had before. I'm going with a strong bulky base. The bulkier it is, the less likely it can substitute. So because of that, we kind of lock it in. So a couple things: a really bulky base that can't be a nucleophile, or high temperature. Both of those should be telltale features of elimination. So it's going to go in. When it does, it's going to attack this H. The electrons here are going to become the pi bond between beta and alpha, and the Br is going to leave. So in the end, you get R1 and R2. Notice R1 is in, R2 is out, and R3 is in, R4 is out. Note that this is a planar molecule because you have a pi bond right here. So all those orbital drawings we also did going to come into play here. So there's my pi bond. My two p orbitals overlapped in a pi bonding network. Again, key features: high temp, strong, bulky base. I'm going to add the word bulky because the bulkier it is, the less it's going to be a nucleophile, the more it's going to act like a base. Okay, the key features, things you should note. A strong, bulky base, or a strong, large base, you have to have it. You have to have something to remove the H from a carbon. H on a carbon isn't going to be very acidic, although when it's anti to the Br, because the Br can pull electron density away and things pull in a line, if you will, it can weaken that and make it a little more acidic. So this H becomes more acidic when it's aligned anti to the Br. So strong, bulky base, large, the bulkiness prevents it from acting like a nucleophile, so it cuts down the chance of this being an SN2 reaction. They must be anti to one another because that helps this become a little more acidic, and it also aligns the orbitals correctly. So the big thing is the pi bond. If I look at where these orbitals used to be, notice how similar they are to what we have over here. They simply have to just rotate over, spread out a little bit. But notice they're in the plane just like they're in the plane. So when they're anti, they're lined up to turn into a pi bond more easily, and it makes this H more acidic. Okay. High temp, because we're going to go to something less stable. And then finally, the rate, because we call it a 2, means it depends on two things. It depends on the concentration of the base and the concentration of the alkyl, in this case, bromide, but whatever the electrophile is. So both affect it. So 4 factors that I'm going to repeatedly make a big ordeal about. High temp, strong, bulky base, has to be aligned anti, and the rate depends on both. And honestly, the rate depend on both is probably going to be the least important of these 3 factors. But when you see a large, bulky base with high temp, and the H and leaving group can rotate to be anti to one another, that's when you get this E2 elimination. So let's look at the orbitals a little more closely. So like I said, this orbital right here, bonded H, and this orbital, this sp3, they are already in the plane. So all this has to do is rotate up a little bit. This has to rotate up a little bit, rotate down a little bit, rotate down a little bit, and then share their density a little bit more. So note that they're anti, so they're aligned correctly. The orbitals are in a line. So what happens in this case is when the base comes in, the base is going to come in here. So let me do my base. Sorry, time out. Let me line it up better. This lone pair, I'm going to put into an orbital like this, kind of like we're seeing there. That lone pair is going to line up with this H. So notice that comes in, picks that up. This rotates from there to here. This rotates over to here, shared density, and the Br essentially stays where it's at. So electrons don't move much in this process, but they do go from being shared between an H and a C to being shared between O, the base, and the H. Between the C and the H and the CBr, those now shared between the C and the C, and the Br gets electron. So it gets to take both those bonding electrons, so it now becomes Br minus. So something to keep in mind, we had a minus in this to begin with, we have a minus here. Have to keep track of charge. Okay, take home message again. 3 things you have to make note of when you see it, and just know it's going to be elimination by an E2 mechanism. Strong, bulky base, check. Heat, check now that I've written it in. And then anti-H to the leaving group, check. If you have those three things, you're going to get an E2 elimination. The typical bases, hydroxide, that'll work. A little bit tricky because it's small enough to be a nucleophile, so it's not ideal, but it could work. Methoxide, a little bit bigger, so less chance of substitution. Methoxide gets any bigger, but once you start getting to these really large bulky base, T-butoxide and amide, amide is also kind of small, but it'll still work. But the two we're going to see quite often, I'm going to use quite often, are the bulky base, because you just eliminate any risk of an elimination reaction when you use these bulky bases. So LDA, known as lithium, there's lithium normally here, diisopropyl amide. And then either potassium or sodium will be the countercation, T for tert butoxide. Absolute bulky group, absolute bulky group. So these are the two common bulky ones. These other ones can also get elimination, but you run the risk of some substitution because they're small enough. But because they're so strong, again, you'd rather take a proton than add to a carbon. It's just easier to take a proton. They're so lightweight. Okay, onward we go to an E1. So just like we noted with substitution, the leaving group has a leave first. Same story here. You're going to see me probably use an alcohol that's been protonated about 80% of the time. It works with other leaving groups, but alcohols just really, I don't know, work out exceptionally well. So if I protonate this and have a plus charge here, this can now leave. So again, it's a two-step reaction. So when it leaves, you're going to end up with water. So this water is going to be off on its own, H2O. And you have this carbocation. Again, have to consider the carbocation to make sure I know it's going to rearrange or not. Tertiary carbocation is stable. If this H moves over, it's a tertiary. So it might move over just because of entropy, randomization, but not because it's getting any better. If you moved over and it got worse, so if you went from tertiary to secondary, that wouldn't happen. But tertiary to tertiary is just going to randomize. Secondary to tertiary is definitely going to happen because of increased stability. But here, tertiary, so I'm not going to worry about elimination. Rearrangement before my elimination. So do I have all the features? I have high temp. Do I have anti? And guess what? It ends up I don't need anti in this one. Eventually I have to get the H lined up the right way for the orbital, but it doesn't have to start out anti because it's not coming off all at the same time. It's happening one at a time. So one less stipulation, but the high temp is still there because you're generating a less stable product. Okay? To go from here to here, you have to get rid of that H. The H is going to eliminate over. I will point out that it is much better when this hybrid is aligned with this empty p orbital. So electrons can just scoot over to that. So that does help. So the H does eventually have to line up, but it could also line up on bottom and rotate over to the other orbital. But it has to be coplanar when it does eventually eliminate, which means we can predict which way these groups will be based on lining the H in the plane. Similar, but not the same as anti-orientation. It helps because eventually the leaving group leaves and it does need to be anti to the empty p orbital. But coplanar is, we'll just stick with that as a statement. So we have a certain alignment here, but because this thing is free to rotate, H could have been on bottom, we could eventually get these things crossed over. So it could be R2 up here and R1 down here. You get a mixed bag, just like you did with SN1. Key features: strong acid, could be a Lewis acid. We are so used to seeing H2SO4 and nitric acid as strong bronzide-Lowry acids, the ones that donate an H plus to a leaving group. But you never know, you might see silver. Ag plus accepts electron density from a halide. That could be your strong acid. So your strong Lewis acid, be open-minded. Anything that can accept electron density or protonate an alcohol. High temp, again, high temp just because you're pushing it in the forward direction, going from sigma bonds, which are stable, to a pi bond, which is less stable. Good leaving group, it won't work if this thing can't first leave. So you have to have a good leaving group. That's an absolute must. And something we're going to call Zaitse's rule. So we're now stepping into that brief comment I made earlier about how substituted it is. Zaitse's rule says the double bond that is most apt to form, most likely to form, is one that is most substituted. So just like before, when we had the possibility of this or this one has 1, 2 R groups on the double bond. This one only has 1. So this is di-substituted. This is mono-substituted. So according to state test rules, that is your major product. You want to form that one. Okay. Potential for rearrangement. Anytime I have a carbocation, I have to worry about how it can move around. And then last but not least, the rate only depends on this molecule. Doesn't matter at all how much acid you put in. It's catalytic in nature, so it just doesn't make a difference. It only depends on that concentration. Add more of this in, reaction goes faster. Okay, I think we're on our way. And at this point, I hope you're sitting there and just taking time. And the best thing about a video lecture, you can take a time out. And if you need to, right about now, to write down everything you need to know, or everything we just said, it's a really good idea. Just honestly, just flashcarding yourself right now, quizzing yourself on those things that matter. High temp, strong bulky base, strong acid. And hopefully you come across some shortcuts and you realize, wait a minute. 1 is the first number, A is the first letter, E1 went with acid. 2 is the second number, B is the second letter, E2 went with base. They both have heat. This is strong and bulky. This one is strong and poor nucleophile. So that's pretty straightforward. That's my key pool of information. It comes with practice, it comes with exposure. Okay, onward we go. So alkene substitution types. So this is what I was trying to make a bigger deal about with Zates rules. An unsubstituted alkene is just ethene. It's got 2 H's here, 2 H's there. There's absolutely no carbons. Next, monosubstituted. The R group can be any of these 4 spots, doesn't matter. There's only 1 R group on the double bond. When there's 2, it can get a little tricky. You can have 2 on the same carbon, or you can have 2 on opposite carbons. And this is cis because they're on the same side. When they're on the same side, they're cis. So it's also known as Z for the geometrical orientation. And then you can also have them across one another, which we're going to call trans. Oh, oops. This didn't work out well. My apologies for this. I'm going to quickly cover it up, even though I thumb bumped the other one. So this is a di-substituted alkene. This one is my tri-substituted. And E or Z all depends on which takes priority. So on this left carbon, I'm going to say that's my higher priority. And assuming R is higher priority than R prime, that means the 2 highest things are trans, hence we call it an E. But that's tri-substituted. And then finally tetra-substituted. Oh, that's C, I apologize. So that's if these 2 groups are the same side. And then finally tetra-substituted. You can have E and Z anytime you have 2 different substituents on each of the double bond carbons. So in terms of stability, mono beats unsubstituted, di beats mono, tri beats di, and tetra beats di. But then also trans beats cis for spacing. So if I consider this one, it's more obvious. Cis, they are kind of crowded here. They're so far away. So trans is more stable than cis. They're both more stable than this group because these are way too close and they'll bump into each other. And then for this one, typically E, the bulkier groups, if it's based on bulk, is more stable, but I don't want to commit to anything because I don't know exactly what the groups are that cause the priorities. Okay, key thing, no H's, bad, or all H's, no R's, bad, no H's, all R's, good. So most substituted, most stable, least substituted, least stable, and these all fit somewhere in between. Okay, least stable, most stable. Just have to have that down pat. So time to try a question. La-di-da-di, yippee-yahoo, hooray. I love studying for OChem, blah, blah. Very, I don't know, eloquent question, and I'm very proud that I was able to create it. So let's see what I know. So once again, this is one of these things is not like the other. So leading group should be anti to the H being lost. That is known as an E2 feature. E2 makes those anti to one another. The rate depends on the alkyl halide concentration. Well, that is actually both E1 and E2. The only difference is E2 depends on base, the E1 does not. The reaction requires the addition of a strong bulky base, E2, and rearrangement is observed during the reaction. This, unfortunately, is where my technique breaks down. All I can tell you for sure is that it's probably not C and probably not A because they match. But now I have a difficult decision. I actually have to go back and truly understand the question. It can't appear like that to me. I have to actually break it down. But if it's something that says, what's a dual feature? That's that. Or if the question deals with something that uniquely makes it E1, then I can eliminate the 3 that have E2 features. So again, this is a judgment call. I was in the mood to make it an E1 different than all the rest. But if the question had to do with which one can be seen with both mechanisms, then B would have been your better answer. So one of the things, not like the other approach, although genius, I thought, apparently can fail sometimes. But it's better not knowing. Okay, heat. Notice the fire that kicked in, higher than room temperature. Room temperature should be 25 degrees Celsius approximately. So when you raise the temperature, you're going to drive a reaction to go forward. For this first one, the Cl is a leading group, and that's my H. So I'm going to get those two. They are anti because if that's up and that's down, then they can be anti to one another. That's your major product. But you could potentially also get this product because it could have taken the H from over here. The reason it doesn't do it as much, the reason I'm going to call that a minor product, is because it's the less substituted. So this one is tri-substituted. It's got a group there, there, and there. This one is just di-substituted. So that's your major product here. That's your minor product. It's a little tricky on this one because these two are cis, and therefore they cannot be anti. Only trans on a cyclohexane like this can be anti. So because they're cis, this H can't be lined up the right way, so you can't get elimination. So the only H possible that's going back is this one, which means this is not only your major product, but it's kind of your only product. There is no other H, no other beta you can take. So here's my alpha carbon. This beta has one going back that is trans to the Cl, so it works. This one is cis, it will not work. And finally, the last reaction, this one, H2SO4, should be your dead giveaway of acid. So A1, B2, B2. So this is an E2 reaction, E1 reaction in acid. E1 forms a carbocation and can get rearrangement. So mechanistically, I'm going to blow through this kind of quickly, but if this H goes there in the water and this leaves, you now have a carbocation on this carbon. Actually, let me write this a little bit better. And that H that's being showed so proudly there can rearrange over. So I'm now going to end up with my plus charge now on this carbon. And then I can eliminate this H and get a double bond that is 1, 2, 3, 4, tetra-substituted. 1, 2, 3, 4. So this double bond right there is one will form. So the key thing, though, question isn't so much on that. This is just added detail that I need to go into for my own sanity. I needed to just know rearrangement. Rearrangement is an SN1 or an E1 phenomenon because I'm dealing with high heat and an acid that's a terrible nucleophile. It can't be SN1, it's an E1 reaction. So E1 can only be associated with reaction 3. So E1 elimination. So strong base is E2, so those are out. Strong acid is E1, so that's in. Best answer is acid eliminates. B is in, boy, that's the only possible choice left. Okay, so I went into far more detail on this question, which is fine. We should be doing that sort of thing. Okay, for this one, why do reactions 1 and 2 yield different major products? Okay, so again, strong bulky base, E2, strong bulky base, E2, high temp. So my double bond is more substituted and less substituted. Again, it's because these are trans. Actually, let me write this better, and I'm actually going to start by choosing a slightly better color. Trans. And these are cis, which means I have to take this H. So I just answered on the earlier question without realizing I was answering the question in advance. But the only way you can get trans is to go to the other side. So they proceed by different mechanisms? Nope, E2. Strong bulky base is E2 no matter which side it goes to, so that's out. They proceed by a syn elimination process? Nope, it's not the same side, it's always anti, that's out. They proceed by anti, resulting in different products. That's looking the best so far. They start from different structural isomers. These are stereoisomers, all the same bond conductivity. Difference is a stereocenter here versus stereocenter there. So these two are diastereomers, to be specific. Okay, so they're both E2. They do not go by syn, they go by anti. So best answer, C is in. Cool, kind of getting this, but a lot is being thrown at you. This is a new reaction, and I encourage you when it comes up in class to ask every possible question you can to feel a little more solid about it. And in the end, when everything's said and done, you're going to realize there is a certain amount of memorization. Strong, bulky base, high temp, anti. That can get elimination. Strong, bulky base, high temp, anti here. So that's what I'll get. So trans can become anti. I'm calling it trans and cis because it's this drawing, but if I drew it in the chair, I would actually see the anti when it's trans. Ooh, another question. It seems like the same thing is same set of reactions over and over. So which of the three reactions generates an optically active compound as major product? So I have a chiral center here still. I have chiral centers here. This one, no chiral centers left. So in the original molecule, I have 1, 2, 3 in each one of these. Elimination got rid of 2 but left 1. Elimination got rid of just 1 and left 2 in this one. And this one got rid of all 3 with a rearrangement. So still optical, not optical. So 1 and 2 only. So let's see what the screen pops up when I punch it. Let me get rid of my writing. So going in 3, 2, 1, and clear. So just like you said, this is chiral, this one and this one, both of these are, but nothing's chiral here. So best answer, C is in. Cool. That wasn't so bad. So these multiple choice questions aren't that bad, and they are hopefully getting me to think about these things. So I'll toss one more, and I'm pushing multiple choice because it's actually a really good way, going through the wrong answers, to discuss what is right and what is wrong. So there is actually a method to my madness. Got to go through the mechanism on this one. So when the following reaction is carried out, why does optical activity disappear? So in the very beginning, I must note that I have 1, 2, 3 chiral centers. To have all optical activity disappear, all of them have to be lost. So mechanistically, I need to figure out what the heck is going on. So I apologize in advance because I'm going to just ignore stereochem because I know it's gone in the end. I'm going to put a CH3, CH3, and an OH, and going to completely ignore the existing stereochem. First step, I'm going to protonate. Acid catalyzed, catalysis means the enzyme or catalyst goes on immediately, goes on first step. So I'm still the same backbone, still the same CH3, CH3, but now I have OH2 plus. We've seen before water leaves. So when that happens, I now have CH3, CH3, and a plus on a secondary carbon. There's an H here that I need to write in. I'm going to change color on it, actually. I'm going to make it green. That green H right there is free to undergo rearrangement. Those electrons can go attack that carbon. So now I have plus there, which is tertiary, which is much more stable. And if I get elimination, so I'm going to eliminate from this hydrogen because that will give me the most stable. And I need to go ahead and finish this. I was ignoring my ethyl group. You're gonna have to trust there's a 3 there. So once I eliminate that H, it will go up to be product of there, drew too big an arrow. The major product is CH2, CH3, CH3, CH3. Ah, shoot, just butchered that one. And double bond there. So we ended up eliminating all the chiral centers because of rearrangement and elimination. So I'm going to click and see what pops up. So let me erase my drawing. You can hopefully go back and clean it up in your notes and just say, this is the product we're going to get. So notice that the OH got eliminated, rearrangement brought over in unit with a safe product. So how do I say that with these answer choices? E2? Nope, because acid is E1. Acid begins with an A. A is the first letter, so E1. So no to that. Alkenes cannot be optically active, not true. You can have an alkene that has another atom with a chiral center on it. Because the reaction forms a racemic mixture, always a good choice. It was substitution, but it's not. Because rearrangement, elimination take away all the chiral centers. Exactly it. So just what we came up to. So that's out, that's out, and that's out. Best answer, D is in. Dang, that's a tough question. Again, I'm trying multiple choice so that we go through what is wrong on the way to learning what is right. And there's actually a lot of power in learning that way. So these are challenging questions for a topic you haven't seen before, but hopefully some of the things are sticking. We're all done for now, but one of the things you need to do is make a list of the features for E1 and E2. Strong, bulky base, strong acid that does not act like a nucleophile. Heat, anti-H/leaving group. This one is just a good leaving group. Couldn't help from being protonated. And there's other factors we go into, but you should recognize the base for 2, acid for 1, strong, bad nucleophile, strong and bulky, so it's a bad nucleophile. So it have to be bad nucleophiles so they don't substitute. Acid is 1, base 2, heat, anti-H, good leaving group. So I will see you at the next podcast. I hope this one went well. This is one you may have to slow down and pick up the things. It's not that it, again, like so many things, it's not like it's hard once you get the hang of it, but at first glance, this can be very confusing and quite honestly, information overload. So keep things simple. And when you come into lecture, you should have this concept written down in advance. These should all be available to you so you just know what to look for. E2 and E1, call them out as they show up in class. Okay, so have an absolutely wonderful, wonderful day. I hope I can get this to let me out, but I think I'm just going to have to shut it down in a weird way. So you're going to see my computer screen, which I don't want. There we go. So it finally did it. So I'm going to stop recording and I will see you at the next one.